All right, example number 2, it says a student dissolves 10 grams of NaOH, so sodium hydroxide, in 100 milliliters of distilled water, and notices that the temperature of the mixture increases from 25 degrees Celsius to 51.6 degrees Celsius. All right, so I'm going to go ahead and underline the most important pieces of information there. We have 10 grams of sodium hydroxide in 100 milliliters of distilled water, and the temperature increased from 25 to 51.6. So we might need those for later parts of this example. So A, it says the student states the process of dissolving sodium hydroxide is endothermic because the temperature increases. So the change in temperature is a positive number greater than 0, and so therefore Q has to be positive greater than 0. It says, do you agree or disagree, and why? It says use the system, surroundings, heat, endothermic, and exothermic in your explanation. All right, pause it, think it through, and resume the video when you think you might have something to say about it. So this part right here is the sodium hydroxide dissolved in the water. That's going to be our system, right? And then the actual sodium hydroxide, right? All of this right here, that's a sodium hydroxide being dissolved, and like the powder at the bottom is sodium hydroxide. The actual water itself, so it's dissolved in 100 milliliters of water. That will be our surroundings, right? So I'm defining the system as the actual sodium hydroxide and the surroundings as the water in which it dissolves in. And so it says the student observed the water increasing in temperature, right? And so in order for it to increase in temperature, that means that heat had to go from the system, the sodium hydroxide, into the water in order for it to increase the temperature of the water, right? And so if we increase the temperature of the water, it had to have energy added into it. If it was energy added out or taken away from it, it would have decreased. So if it's energy going into the water to increase that temperature, it's going to be exothermic because it's going out of that system. Remember, exo means out. So the energy goes out of that system into the surroundings, and then it increases that temperature. There you go. So see if you got it right, and if you didn't get it right, make some corrections of what were your misconceptions. For B, it says explain in terms of molecular motion what is happening when the temperature of the water is increasing. And so for this one right here, the heat that's transferred into the water increases the molecular motion of that water, right? So the energy used to increase the molecular motion or the kinetic energy of the water comes from the temperature from which the sodium hydroxide released, right? And so whenever you have something going from solid, so we had sodium hydroxide solid, and it went to sodium hydroxide aqueous, meaning it dissolved in the water, right? Aqueous meaning water, agua. Whenever that happens, you're breaking it apart, right? It turns into sodium, which has a positive charge, and hydroxide, which has a negative charge. You had to break that bond in order for them to dissolve in the water. And so whenever you're breaking something, you have to add energy into it, right? And for this, it increased the temperature of the water. And so it released that energy into the surroundings, increasing that temperature. And that temperature, remember, is average kinetic energy. Go ahead and write that. Temperature is average kinetic energy. And so if you're increasing the temperature, you're increasing the average kinetic energy. Kinetic energy is just motion. And so if you're increasing the motion, you increase the temperature. All right. The next part says describe pictorially the substances before NaOH solid and H2O liquid and after the dissolution, so NaOH aqueous, and identify the interparticle forces, so the intermolecular forces are interparticle forces, involved in the substances before and after the dissolution. Do the substances before the dissolution have less or more potential energy than those after the dissolution? And so before we had our sodium hydroxide, right? And so we had, let me go ahead and draw sodium hydroxide, it's together, and we had H2O together, right? And they weren't mixed, they were separate, right? And so we could draw out the Lewis structures of those if we needed to. Afterwards, right, they're splitting apart in the water, right? So we had So beforehand, our structure of sodium hydroxide is positive with the negative, and then it's an alternating lattice structure, right? The positive and negative charges align each other, right? And you could draw a whole bunch of them. I'm just drawing a couple because that's the only space that I have. When you put it into the water, that salt, that sodium hydroxide, breaks apart, and we have sodium positive and hydroxide negative, right? I'll draw the molecules around them. On the AP test, make sure you're drawing the anion, the negative charged anion, a little bit bigger than the cation. That's just correct representation in general. The water that forms around it, the negative oxygen will be around the sodium, and that is because oxygen is slightly negative. So I'll draw one more. If my pen will work right here. There we go. Right, and so it's slightly negative, whereas hydroxide is slightly negative, so the hydrogens will be around the hydroxide. And that's because hydrogen is slightly positive and it attracts towards the negative hydroxide. So before we have ionic bonds in sodium hydroxide, we have covalent bonds in water. The interparticle forces that we have in sodium hydroxide is ionic. The interparticle forces we have in water beforehand is hydrogen bonding. Afterwards, when it splits it apart, we have covalent bonds still in the water. We have hydrogen bonds between water molecules. But then this right here is an ion with a dipole, right? Because the dipole comes from the slightly positive and slightly negative charges from water and from the oxygen. So dipole meaning two poles, meaning opposite charges. So we have a partial positive from hydrogen, a partial positive from oxygen, and that's a dipole. So we have an ion-dipole interaction right there. We also have an ion-dipole interaction between the hydroxide and the positive hydrogens. Right? And there you go. And then the potential energy, it says, do the substances before the dissolution have less or more potential energy? And potential energy decreases because it's an exothermic. It will increase if it's endothermic. All right, for D, it says, describe the process of breaking and forming interparticle forces, attractions, in the dissolution of sodium hydroxide. Draw a potential energy diagram for each step, the process, and then explain why the temperature lowers when dissolving a different salt. So for the first step, for sodium hydroxide, we had to actually break the NaOH ionic bond, right? So we had to break NaOH bond, and it's an ionic bond because of its a cation with an anion. And so that step right there is endothermic, right? We have to put energy into it in order to break it. And so we're gonna we start off kind of like randomly right here, and we put energy in to break that step, to break that ionic bond between sodium and hydroxide. Second, we had to break the hydrogen bonds between water. Right, and we're not talking about the covalent bonds, we're talking about hydrogen bonding. And remember, hydrogen bond is a force, it is not an actual bond. Right, it's a bond, it's a force though. It's just called hydrogen bond. And so we had to break that water bond, and that requires energy putting into it, so that is also endothermic. Right, so we're here now, we put some more energy into it, that's endothermic, so this is our first step, this is our second step right there. After we broke the sodium hydroxide ionic bond, and after we broke the intermolecular force, the hydrogen bond, the hydrogen force between the different water molecules, the next thing we had to form was the ion dipole attractions between the sodium positive cation and the hydroxide negative anion. And so we formed, and I have to use my finger to write because my pen is not responding very well. So if this is a little messy, I'm sorry. So we formed the sodium with the water, right? So H2O, I'm going to draw it with oxygen facing towards sodium because the oxygen is partially negative, so it attracts to the positive cation. And that right there, when you form something, that's exothermic. We also had to form the hydroxide anion to the water, right? That's going to be attracted to the partial positive, the hydrogens. That is also exothermic. And so we're now here on our graph, we go down a little bit. That's our third step. And then we go down a little bit more. That's our fourth step. And notice that I drew the fourth one a little bit lower than the first step because overall our process is exothermic, right? So products minus reactants, it's going to be a negative number, and so we need to draw it a little bit lower. And so dissolving something like ammonium chloride in water is going to be endothermic because it has a stronger ionic bond and it has weaker dipole-dipole attractions, and that's just due to the atomic size and electronegativity of a certain compound. All right, for E it says calculate the heat flow Q. For this process, the specific heat of water is given. And so we have our simple equation. We have Q equals MCAT. And so our mass was given to us way up above. It was 100 grams. So go back to the beginning. It was 100 grams of water. There we go. My iPad is not responding very well right now. Our specific heat of water was given to us, 4.18 joules per gram degree Celsius. Okay, that's given to us right there. And then our change in temperature is also up above at the previous, the very, very top in example 2. It's 51.6 minus the 25 degrees Celsius. And when you plug this all into your calculator, you end up with 11,100 joules. And it's going to be a positive number. So it is endothermic. All right, and then for the next one, it says calculate the delta H, so the enthalpy of dissolution. So DISS is dissolution for this process going from solid to aqueous. And we know that the Q of the reaction is equal to negative Q of water. And we know that the negative Q of water was we just calculated it, right? This is for water. Wow. There we go. And so if we plug that in, we know that the Q of the reaction is just equal to negative 11,100 joules, right? We know that delta H from our unit 2 previous semester, that delta H is just Q over N of the reaction. So our Q is the negative 11,100. And we have to find the moles of the sodium hydroxide. In order to find the moles of sodium hydroxide, we need to just do a simple mole conversion. And so moles of our reaction, which in this case is our sodium hydroxide because that's how we defined our system. We started off with 10 grams of sodium hydroxide. If we multiply it by our molar mass, so we put 40 grams on the bottom for every 1 mole, we end up with 0.25 moles. So plug in your negative 11,100 on the top, plug in your 0.25 moles of sodium hydroxide on the bottom, and you're going to end up with about negative 44,500 joules per mole. If you wanted to, you can convert that into kilojoules. There you go.